Hi, and welcome back to Tactical DevOps. I'm Joe.
And I'm Jane. Today, we are taking a look at storage in Kubernetes.
So let's just jump right in. Imagine this scenario for a second. It is Black Friday,
Oh, boy.
right? Or, the launch day of your biggest feature of the year. Web traffic is spiking totally off the charts, and your primary database container suddenly crashes under the immense load.
Which happens to the best of us.
Exactly. And you might think, well, no problem. Kubernetes is literally designed for this, right?
Right, self-healing.
Yeah. And sure enough, the system beautifully spins up a replacement container in milliseconds. But when it boots, all of your customer transaction data is gone.
Just completely wiped clean.
Wiped clean. The application is up, but the state is completely destroyed. And honestly, if you don't understand how Kubernetes handles data persistence, that nightmare scenario is just your default reality.
It really is. And that default reality stems from the fact that originally Kubernetes was fundamentally designed around stateless applications.
Right.
When you just spin up a pod, do some processing, and let it die, I mean, the system absolutely shines.
It's perfect for that.
But the moment you introduce stateful workloads, so databases, message queues, really anything that needs to remember what happened 1 minute ago,
Yeah.
you are fighting against the innate ephemeral nature of containers.
You're pushing against the grain.
Exactly. So the core concept we really need to explore in this deep dive is storage decoupling. Because, in a legacy virtual machine world, the hard drive is physically and logically tied to the server.
Right. They are one and the same.
Yeah, but Kubernetes completely breaks that link.
So we are essentially separating the life cycle of the actual physical disk from the life cycle of the pod itself.
We are. And doing that allows developers to guarantee data integrity even when pods crash, restart, or just get violently rescheduled to entirely different hardware across the cluster.
Which is a massive paradigm shift. You're moving from tightly coupled, fragile infrastructure to a truly resilient data model.
It really is.
And look, if you are listening to this and thinking, well, why do I need to learn this if my team just uses managed cloud databases? Please stick with us.
Oh yeah, you still need this.
Right. Because even if you outsource your main database, your applications still need to securely mount secrets or access configuration files or even cache data, and all of those use this exact same volume architecture.
100%.
So let's start at ground zero here. What happens if you just deploy an Nginx container and start writing files directly to its local file system?
Well, you are basically living on borrowed time.
Yep.
The file system inside a standard container is built on temporary image layers. It literally only exists for the specific lifespan of that exact container instance.
So if it crashes?
If the container process crashes, the kubelet agent on that node will, of course, restart it to maintain your desired state.
Right.
But it restarts with a completely clean slate.
Wow.
Yeah, any log files, uploads, or configuration changes that were written to that local file system are permanently gone.
Okay, but Kubernetes does offer some built-in basic volume types to sort of mitigate that slightly, right? Like the empty dir volume.
Yes, it does.
I always like to compare an empty dir to a rolling whiteboard in a hotel conference room.
Oh, I like that.
It's fantastic for temporary scratch space while your team is, actively in the room having a meeting. All the containers inside that specific pod can read and write to the same empty dir, so they are effectively sharing that whiteboard.
Right, they can all see the same notes.
Exactly. But the moment the meeting ends, like the moment the pod is evicted, deleted, or moved, the hotel staff comes in and wipes the whiteboard completely clean.
Yep.
And obviously, you would never put your permanent financial records on a hotel whiteboard.
No, you definitely wouldn't. And actually, if we stretch that whiteboard analogy just a little further, the physical markers you use actually matter quite a bit here.
Oh, how so?
Well, by default, an empty dir volume writes directly to whatever storage medium the host node is using. So whether that is a standard spinning disk or a fast SSD.
Okay, that makes sense.
But you also have the option to set the storage medium to memory. This tells Kubernetes to mount a teamfs, which is essentially a RAM-backed file system.
Okay, I can see the appeal there. I mean, RAM is exponentially faster than a disk.
Oh, absolutely.
So if I have a container doing really heavy temporary image processing, a RAM disk sounds totally perfect, but, and correct me if I'm wrong, I imagine there is a massive catch there.
There is a really critical danger with RAM-backed volumes. You must absolutely must explicitly configure a size limit in your manifest.
Okay.
Because without a size limit, there is no upper bound on how much memory that file system can consume.
Oh, wow.
Yeah, so a runaway process inside your container could just keep writing temporary data until it devours the pod's entire memory allocation. Or even worse, it exhausts the available physical memory on the host node itself.
That seems like a fast track to taking down a server.
It is, because when the Linux kernel detects that memory starvation, the operating system's out-of-memory killer steps in.
And the ohm killer is notoriously ruthless. It will just start terminating processes left and right to save the node, potentially taking down your actual workload in the blink of an eye.
Exactly.
So, note to self, always cap your RAM disks.
Always.
Now, there is another primitive volume type I often see creeping into, like legacy setups or maybe local development environments, which is host path.
Oh, host path.
Yeah, this essentially lets you punch a hole directly from the host node's physical file system into your pod, right?
It does, but while host path exists, relying on it in a production environment introduces severe security and architectural flaws.
Really? Like what?
Well, let's look at the security aspect first. If you allow developers to write pod manifests that mount arbitrary directories from the underlying physical node, a compromised container could just mount the node's root file system.
Wait, really? So an attacker breaks into some vulnerable web app container and suddenly they can read the host server's shadow password file?
Yep. Or they could access the Docker socket.
Oh, that's terrible.
Right. They could easily orchestrate a complete container escape, elevating their privileges to gain total control over the underlying infrastructure.
That is a massive red flag.
And beyond the security nightmare, host path completely destroys the portability of your workload.
Because it's tied to that specific node.
Exactly. If your pod requires a specific file path to exist on node A, and the scheduler tries to move that pod to node B, where that path hasn't been manually created, well, your application permanently fails to start.
Right. Okay, so if MTDR is just temporary scratch space and host path is a huge security risk, how do we get actual durable storage?
Good question.
And this brings us to the core abstraction of Kubernetes storage, right? Persistent volumes and persistent volume claims.
Yes.
Which, I gotta say, when I first encountered this, it felt like a wildly complex, unnecessary two-step dance.
It totally looks overly engineered on the surface, I agree. But the underlying logic solves a massive organizational problem.
Okay, break it down for me.
Sure. Let's define the two distinct pieces. First is the persistent volume, or PV. This is a cluster-level resource representing a physical piece of storage infrastructure like an actual hard drive that is provisioned by a cluster administrator.
So it's the physical hardware side of things.
Exactly. And it exists independently of any single pod. Second is the persistent volume claim, or PVC.
The claim.
Right, the claim. This is merely a request for storage made by a developer or an application.
Yeah.
The PVC basically says, hey, I need 10 gigabytes of storage with read-write access.
So Kubernetes basically acts as a matchmaker here.
That's a great way to put it.
The developer hands in their PVC claim check, and the control plane looks around the cluster for an available PV that meets those exact requirements and then binds them together.
Exactly.
But let me push back on this a little bit.
Go for it.
Why this convoluted separation? Like, if I know for a fact I'm running on AWS, why can't I just put the AWS Elastic Block Store ID directly into my pod manifest and just be done with it?
Because doing that tightly couples your application code directly to that specific cloud provider's infrastructure.
Okay.
Imagine your engineering team writes hundreds of microservice manifests with hard-coded AWS volume IDs.
Right.
A year later, your company signs a massive contract with Google Cloud, or maybe they decide to move everything to an on-premise data center using an NFS server.
Oh, I see where this is going. I would have to go in and rewrite and retest every single deployment YAML in the entire company just to change the hard drive configuration.
Exactly, and that is a nightmare. The separation of concerns eliminates that refactoring entirely.
That makes a lot of sense.
The developer writing the application doesn't need to know, and honestly shouldn't care, whether the underlying disk is an EBS volume, a Google persistent disk, or a fiber channel SAN.
They just write the PVC and move on.
Exactly. The cluster administrator manages the actual hardware via the PVs, so the application remains perfectly portable across any environment on Earth as long as the local cluster admins are providing matching PVs.
Okay, that completely justifies the abstraction for me. So once the matchmaking succeeds and the PV is bound to the PVC, we have to determine how the pod can actually interact with the data, right? Right. Which introduces access modes. And looking at the sources, the documentation lists several acronyms here that look like a total bowl of alphabet soup. Let's break down the actual mechanics of why these distinct modes exist.
Sure. So the limitations around access modes are largely dictated by the laws of physics and the underlying storage protocols.
Sounds intense.
Well, the most common mode is read-write once, or RWO. This means the volume can be mounted as read-write by a single physical node in the cluster.
Just one node.
Right. Standard block storage, like a typical cloud hard drive, physically cannot be attached to two separate virtual machines at the exact same time without completely corrupting the file system.
Oh, because they'd both be trying to write to the same blocks.
Exactly. Therefore, if you use block storage, you are strictly restricted to read-write once.
Which is perfectly fine for, a standard single replica database. But what if I have a deployment of, say, 5 web servers that all need to read the same massive directory of static images?
Then you would use read-only many, or ROX.
Okay.
In that mode, multiple nodes can mount the volume simultaneously, but strictly in a read-only capacity.
Got it.
If you actually need multiple nodes to both read and write to the same volume concurrently, you need read-write-many, or RWX.
And you can't achieve RWX with a standard cloud hard drive, right? You would need specialized network-attached storage for that.
Right, something running over IP, like an NFS server or maybe Amazon EFS.
Because it has to be designed to handle simultaneous distributed write locks.
That is exactly correct. And recently, the community actually introduced a much stricter mode called read-write-once pod, or RWOP.
Read-write-once pod, how is that different from regular read-write-one?
Well, while standard read-write-once restricts access to a single node, technically any number of pods running on that specific node could mount the volume. Read-write-once pod locks it down entirely. It ensures that only one single specific pod across the entire cluster can access that volume.
Wow, so that offers maximum data isolation for highly sensitive workloads.
Exactly.
Okay, so we have to talk about what happens when an application is repired.
Good point.
Let's say I delete my PVC. What actually happens to the data sitting on the PV? The sources explain this is handled by reclaim policies, specifically retain, delete, and recycle.
Right.
Now, retain seems obvious. The data stays there until an admin manually cleans it up. Delete tells the cloud provider to literally destroy the underlying disk.
Yep.
But recycle sounds like an incredibly efficient, eco-friendly option. Why does the documentation heavily flag it as deprecated?
Well, the reality of the recycle policy was crude and highly insecure.
Really?
Yeah. When a PVC was deleted, the recycle policy basically instructed Kubernetes to run a very basic scrub command on the volume,
What kind of scrub command?
essentially executing a recursive arm arrayf command to delete the files.
You're kidding.
Nope. And that it would immediately hand that exact same physical volume over to the next PVC that requested storage.
Wait, just a basic file deletion. Anyone who has done basic data recovery knows that deleting a file pointer doesn't actually wipe the sectors on the physical hard drive.
Exactly. Which is a massive liability in a multi-tenant environment. You cannot rely on a simple directory scrub to isolate data between different teams, or worse, different customers.
That's terrifying.
It is. So the modern secure approach is entirely driven by the delete policy, which is usually paired with dynamic provisioning.
Okay, how does that work?
When you need storage, a brand new, cryptographically clean physical volume is generated on the fly. And when you delete the claim, the cloud provider completely destroys that specific volume. No recycling.
That makes way more sense. And that actually perfectly transitions us to the administrative bottleneck.
Oh yes, the bottleneck.
Because if a massive enterprise is spinning up and tearing down thousands of test environments a day, an infrastructure admin manually clicking around a cloud console to create static PVs is going to grind development to a total halt.
Absolutely.
The system desperately needs automation there.
And the solution to that bottleneck is the storage class.
Yeah.
A storage class is essentially an API-driven template. It tells Kubernetes exactly how to dynamically provision storage on demand utilizing a specific driver.
I like to think of creating static PVs by hand, like a housing developer building 50 identical homes in a neighborhood, crossing their fingers and just hoping buyers eventually show up.
Right. It is a massive waste of upfront resources.
Exactly. Dynamic provisioning with a storage class is more like hiring a custom home builder who only pours the concrete foundation the exact moment you sign the contract.
That's a great analogy.
The physical infrastructure only springs into existence the second the PVC demands it.
And to take your custom home builder analogy even further, the builder has to know exactly where to pour that foundation.
Oh, right. Location matters.
Which brings us to a critical and honestly often misunderstood configuration within the storage class, the volume binding mode.
Right, where you're generally choosing between immediate and wait for first consumer.
Exactly.
Well, I'll play devil's advocate here. Immediate sounds way faster. If the developer submits a claim, I want the disk created right away so the pod can boot. Why would I ever intentionally tell Kubernetes to wait?
Because if you don't wait, you can run headfirst into topology constraints.
Okay, explain that.
Well, modern production clusters usually span multiple physical availability zones, let's say Zone A and Zone B.
Got it.
If your storage class is set to immediate, the moment the PVC is created, the cloud provider provisions a hard drive. Let's say that hard drive physically lands in the Zone A data center.
Okay. Disk is in Zone A.
Right. But a fraction of a second later, the Kubernetes scheduler analyzes your pending pod and realizes, uh-oh, Zone A is completely out of memory resources. I must schedule this pod onto a node in Zone B.
Ah. And a physical hard drive sitting in a rack in Zone A physically cannot be attached to a server sitting in Zone B.
Exactly. The pod will be stuck forever in a container-creating state, failing to mount the volume.
That's incredibly frustrating.
It is. But by setting the mode to wait for first consumer, you force Kubernetes to intelligently delay the creation of the physical disk until the exact moment the pod is scheduled to a specific node.
So it waits to see where the pod lands.
Right. The storage provisioner looks at where the pod is going to live and ensures the new hard drive is created in that exact same availability zone.
It's the system deliberately delaying a commitment until it has the full architectural picture. I love that.
It's very smart.
Now, before we move into troubleshooting, we really need to acknowledge that storage isn't purely for databases. Kubernetes relies on volumes to securely hand environment variables, configuration files, and API keys to applications, right?
It does. You achieve that by mounting config maps and secrets as volumes directly into the pod's funnel system. This is really the cornerstone of decoupling your application's source code from its environmental configuration.
But there is a vital security mechanic here regarding secrets, isn't there? Because if I mount a database password into my container, I absolutely do not want that password written to a physical disk where it might be backed up, snapshotted, or just left behind.
Oh, absolutely not. And Kubernetes explicitly prevents that.
How so?
When you mount a secret as a volume, the system automatically backs it with tiers. It lives entirely in the node's volatile RAM.
Okay. That's a relief.
Furthermore, secret volumes are strictly mounted as read-only. Your application can read the database password to establish connection, but a compromised application cannot overwrite the secret or tamper with the configuration.
Okay, so if we look at the big picture here, the Kubernetes control plane is juggling local disks, volatile RAM, Amazon EBS, Google persistent disks, NFS servers, and like dozens of other formats.
It's a lot to manage.
It really is. How does the code base actually manage all of those different dialects? The source materials heavily emphasize the transition to the Container Storage Interface, or CSI. Why did Kubernetes fundamentally change how it handles storage drivers?
Well, it was a necessary evolution to protect the stability of the entire cluster.
Why were they unstable before?
In the early days of Kubernetes, all the code required to talk to AWS or Azure or VMware storage was built directly into the core Kubernetes code base.
Oh, wow.
Yeah, these were known as in-tree plugins. And the bottleneck there was agonizing.
I can imagine.
If a storage vendor discovered a critical data corruption bug in their driver, they couldn't just release a quick patch to their customers.
Because their code was compiled into the Kubernetes core, right? So they literally had to wait for the next official Kubernetes release cycle, which might be months away.
Exactly. By adopting the container storage interface, Kubernetes established a strict, standardized API boundary. Storage drivers are now entirely out of tree. Third-party vendors build, patch, and release their CSI plugins completely independently of the Kubernetes project.
Which means significantly faster bug fixes for users.
Right. And it also stripped millions of lines of third-party vendor code out of the core Kubernetes binaries, making the control plane lighter, more secure, and honestly far easier to audit.
That is a massive win-win. Okay, so we have covered the philosophy, the architecture, and the interfaces. Let's get down in the trenches here.
Let's do it.
How do you actually deploy this? And more importantly, what is your process when a deployment inevitably breaks at 2 in the morning?
Well, it all starts with the YAML manifests. Beyond the standard API version, kind, and metadata, the really crucial configurations happen inside the spec block.
Right.
For a PVC, you must explicitly declare your access modes like read-write-once, and under resources.request.storage, you define exactly how much capacity you need.
Okay, so you write your YAML, you apply it, you clear your terminal, and you check the status.
Yep.
And there it is. Your PVC is just sitting there stuck in pending. This is the classic DevOps stress test. What is the tactical approach to fixing a pending claim?
So if a claim is pending, the matchmaking process has fundamentally failed.
The system couldn't find a match.
Right. The very first thing you need to investigate is availability. If you are using static provisioning, are there actually any unmatched PVs in the cluster that satisfy both your requested capacity and your access mode?
That makes sense.
And if you are relying on a storage class for dynamic provisioning, maybe you just misspelled the storage class name in your YAML.
Happens to the best of us.
Or, more deeply, maybe the dynamic provisioner itself is failing to authenticate with your cloud provider.
You know, the ultimate weapon for diagnosing this is the kubectl describe command.
Oh, absolutely.
I see so many engineers just staring at the pending status, scratching their heads. Running kubectl describe PVC along with the claim name is mandatory.
It really is.
The output will give you a list of system events at the bottom, and it will usually tell you in plain English exactly why it is failing. You will see error messages like waiting for a volume to be created or no matching persistent volumes found.
Yeah, the events log really cuts through the guesswork. But let's look at a slightly more complex scenario.
Okay.
The PVC status successfully changes to bound, so the disk exists.
Great.
However, your pod is trapped in a container creating state, throwing errors that it cannot mount the volume.
Oh, man. That usually points to a physical conflict between the nodes and the access modes, doesn't it?
Frequently, yes.
Yeah.
You might be hitting the topology issue we discussed earlier where the physical disk is stranded in Zone A, but the pod is restricted to Zone B.
Right.
Another incredibly common mistake occurs during scaling. A developer creates a deployment with a read-write-once volume and then attempts to scale that deployment up to 3 replicas.
And because read-write-once strictly limits access to a single physical node, the moment those replicas get distributed across 3 different nodes in the cluster, the system physically cannot attach the disk to the second and third nodes.
Exactly. The first node locks the volume, and the other pods will permanently fail to mount it.
That is a classic gotcha.
It really is. Now, if you step back and notice that storage provisioning is failing cluster-wide for every single team, well, the issue isn't your YAML.
Oh boy, that's a bad day.
Yeah. You need to pull out kubeadm and inspect the health of your control plane. Is the QAPI server successfully routing requests to the CSI drivers?
And more importantly, is the etcd backing store healthy?
Exactly. etcd is the ultimate source of truth. If the database holding your cluster state is corrupted, out of sync, or failing to elect a leader, the entire storage orchestration process will immediately grind to a complete halt.
Wow, okay. So to synthesize this journey, we started by looking at the default, highly ephemeral nature of containers and how basic tools like emptydir give us temporary scratch space. We explored how Kubernetes elegantly solves permanent data retention through the decoupling of PVs and PVCs, allowing developers to request storage without ever touching the underlying infrastructure.
Yep.
We dug into why access modes are dictated by hardware limits, the automation magic of storage classes, and how the CSI standard stabilizes the whole ecosystem.
It's a massive system.
It is. And finally, the absolute necessity of using kubectl described to decode mounting failures in the real world.
The abstraction layers are incredibly powerful once you understand the mechanics beneath them. And honestly, I want to leave you with a final thought based on some cutting-edge developments in the documentation.
Oh, let's hear it.
We briefly touched on the scheduler making decisions based on CPU or memory. Well, Kubernetes is actively evolving a feature called storage capacity tracking.
Storage capacity tracking. Okay.
This allows the scheduler to interrogate the CSI driver to find out exactly how much physical storage capacity remains on a node before it attempts to schedule a pod there.
Which proactively prevents the exact mounting failures we were just troubleshooting.
It does. But think about the broader implications as the industry shifts toward massive AI and machine learning workloads.
Right?
We're talking about stateful applications that require shuffling terabytes of training data across distributed clusters. If Kubernetes can intelligently route compute power based on real-time, highly granular hardware storage metrics, we're no longer just orchestrating containers.
It's true.
We are building highly aware, self-optimizing data fabrics where the compute naturally gravitates to where the data physically fits.
That is incredible to think about.
Right. When the cluster itself understands the gravity of your data, how does that fundamentally change the way you architect the future of your cloud infrastructure?
That is a fascinating question to wrap up on.
Huh.
Lots to think about there. Keep exploring those clusters, and we will catch you on the next deep dive.